Hi guys, in this video I will cover NMR concept number 4 and 5 in the NMR handout. 4 being the coupling, multiplicity, or so-called splitting of the signal. Splitting would be probably the most common term here, or coupling. And we'll also look at the use of the D2O Shake and what that can tell us about our compound. Okay, signal splitting, topic number 4. Of course, when we look at an NMR, but not that one, both signals are singlets in that NMR. But if we back up a bit, typically you're going to find, well, again, singlets here. That's a multiplet, but it's sort of all on top of each other. To go back to some very clear splitting, go back to the two NMRs early on of the two alcohols. And what we see in this top spectrum, which is for one propanol, we have a triplet. It's a signal, but it's split into 3 lines. It's called a triplet. And the integration is given here as 2 hydrogens. That's how I will typically give the integration. We also have a singlet, just 1 line. It's a little broad at the bottom. It's a little bit unusual, but it's a singlet. Here we have multiple lines. If it's more than 4, we're going to call it a multiplet. And then to the far right, most upfilled in the spectrum, we have this triplet. And that's my T, triplet for 3H. Down below we have a multiplet, a singlet, and then a doublet. So the question at this point becomes, why are some signals split, and what makes it a doublet? What makes it a multiplet? That's what we need to look at now. So signal splitting. Okay, we'll start with a statement. Remember, we have B effective. B effective comes from the external magnetic field, but it's modified by local electron density, which opposes the external field, and so the electron density acts as a shielding mechanism. More electron density, the more the nucleus is going to be shielded, and thus more to the right or lower ppm value, the signal will appear in the NMR. Okay, we've covered that. But something else can affect the B effective. Nearby nuclei also have magnetic moments. And the magnetic moments of the nearby nucleophile can affect the B effective as well. So, let's look at an example. This compound here. Consider the signal for the CH3. This compound would have 2 signals, one for the H there, and then one for the CH3. All 3 H's are identical. 2 signals. We've talked about how to determine number of signals. But let's consider this signal here. It turns out that this signal will be a doublet. Okay? Why? Why will that be a doublet? Well, it has to do with the neighboring hydrogens. And in this case, we have one neighbor. Just one. Now that one hydrogen, the nucleus of that hydrogen, has a magnetic moment. That magnetic moment, which has a direction, that magnetic moment can be aligned with the external field, or it can be opposed to the external field. That makes sense. That's exactly what we showed earlier back over here. But look at this. Now again, we're considering this signal. All right. Of course, these H's can also be aligned or with or against the magnetic field. But that's leading to the signal. But while that's going on, the neighboring H's can also be aligned with or against the external field. And when the neighboring H is aligned with the external field, it's adding to the external field. And so this CH3 sees more, or B effective increases for this CH3. On the other hand, you also have molecules in which the neighboring H is aligned opposite the external field. And this is going to subtract from the external field, and so this CH3 feels a lower amount of B effective, or B effective is lower for this CH3. Basically, the nearby nuclei can act to shield. This would be shielding the CH3 because it's opposing. And then opposite of shielding would be de-shielding because this is adding to the external field. Now it turns out that roughly about half your molecules exist in this manner and about half exist in this manner. So really when you are doing NMR of this compound, once you put it in the magnet, you really have two different situations for the given compound. And this leads to really two different signals. But we don't call it two different signals. We call it one signal, but it appears as two lines. It appears as a doublet. One line for each situation. Essentially one line for each B effective. And that's why we get a doublet. Now, that is explained in this cut and pasted diagram over here. Pretty much the same thing I just explained with my own diagram. So you can read that and make sure it fits with what I said here. Okay, let's do another example. What about this compound here? Consider this CH3. Now this CH3 is going to appear as a triplet. Why? Because it has two neighbors. And when we're probing this CH3 by NMR, these two hydrogens, these two neighboring hydrogens can exist in, guess what? 3 different situations. The two H's can both be aligned with the external field, or they can both be opposed to the external field. That's 2 different situations or 2 different scenarios. We could also have one in line with the external field and the other opposing. But then this situation can be sort of duplicated by having the other one in line with this one opposing. Basically, this situation here is twice as likely because there's 2 ways to achieve this situation. Overall, we have 3 different scenarios. 1, 2, 3. This is going to lead to 3 different B effectives for this signal, or for these nuclei, and that leads to 3 different lines. And we call it a triplet. Now, importantly, the middle line of a triplet is twice as tall, approximately, because it's twice as likely for the one up, one down scenario to take place. All right. So basically we're looking at possible arrangements for the CH2 neighbor. And there's 3 possible arrangements. triplet. Okay, let's go back to the original compound. Now let's look at the signal for this H here. This hydrogen, it turns out, is going to give a quartet in the HNMR because it has 3 hydrogen neighbors. And these 3 neighbors can be lined up in 4 different scenarios. The different scenarios, all 3 of these H's, all 3 of the neighbors can be lined up with the external field, or all 3 can be opposed to the external field. But you can also have a scenario where 2 are lined up with the external field and 1 opposed. So 2 and 1. But there's 3 different ways to have the 2 and 1. You can have, if you label these A, B, and C, you can have A and B with, or you can have A and C with, or you can have B and C with the other one being against the external field. But it turns out, since all 3 of these H's are the same, these 3 scenarios are the same. So it's just one scenario, but it's 3 times as likely as that original scenario. Now, we can also have a 4th scenario where 1 is lined up with the external field, but 2 are opposing it. And there's 3 different ways to have that, as shown here. But again, if these H's are the same, these 3 scenarios are each the same. Ultimately, there are 4 different scenarios that are possible for the neighbors here. Boom, 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 and boom. This leads to 4 different B effectives that this H sees. This leads to the signal really being 4 signals or 4 lines. But again, we don't call it 4 signals. We call it 1 signal, but it's a quartet, 4 lines. And importantly, a quartet is a 1-3-3-1 ratio. So this is 1, and then the middle line is going to be like 3 times the height, 3 times the height, and then this. This is your quartet. This is what a quartet will look like. Okay. Ultimately, this all comes from sort of mathematical possibilities for the neighbors. The neighbors have their own magnetic moments. These magnetic moments affect the B effective. But there's different net magnetic moments that are possible. Now, in this, I went from 1 neighbor, 2 neighbors, 3 neighbors. The more neighbors you get, the more sort of possibilities you have for different net magnetic moment coming from the neighbors. All right, that's the theory. Luckily, you don't have to go through this sort of theory and looking at the possibilities each time. We have, this can be sort of boiled down to some math here. The possibilities can be given by a mathematical rule called the n+1 rule. All right? The n+1 rule will dictate or tell you what the splitting will be for your given signal. In the n+1 rule, n equals the number of equivalent, they have to be equivalent, NMR active neighbors. What does that mean, NMR active neighbors? Well, you should know what that means. All right? 2 or 3 sigma bonds away from the nucleus that you're studying or probing at the time. It's limited to 2 or 3 sigma bonds away that the so-called coupling will take place. Coupling. We say that this signal is coupled to this H, and that's why this signal is a doublet. Okay. Now, in certain pi systems, the coupling can take place at longer distance, beyond 3 sigma bonds. Okay? We will possibly see that, but it's going to be sort of an exception. NMR active neighbors. The n+1 rule only works when the neighbors have a spin of 1/2. Now, luckily for us, or an H, the spin of an H is 1/2. Now, most books will not even tell you this information here. But if you ever try to apply coupling to something other than H, you got to be aware that if the other atom has a spin different from I of 1/2, the n+1 rule is not going to work. And we will see an example of this when we look at deuterium, which has an I of 1. Okay, n+1. Let's see how we can use n+1 here, and let's make sure that we see how it works. Okay, let's go back through these again. Consider this signal. What will this signal be? What will be the splitting? It has a hydrogen neighbor. Okay, the H's here. If we draw out these H's, all right, each one is sigma bonded to the carbon. 1, 2, 3. Within 3 sigma bonds, all right, there's another NMR active nuclei. All right. Now these H's are the same. The neighbors, there's one of them. Neighbors is 1. So N is 1. 1 plus 1 is 2. So we expect this CH3 to be 2 lines, and that's a doublet. How about this example? This signal. How many neighbors within 3 sigma bonds? Well, that would be these. 2. 2 plus 1 is 3. This would be a triplet. And indeed it is. Let's look at this H. How many neighbors within 3 sigma bonds? 3. 3 plus 1 is 4. 4 would be 4 lines, and that's a quartet. And indeed, we said it would be a quartet. So the n+1 rule can become a simple rule for predicting your splitting or so-called coupling. Now, a couple of things we need to point out at this point. Does the carbon split the H? All right. We draw this compound here. With the bonds drawn out. These H's are the same. We're talking about this signal. This neighbor affects that signal in 2 different ways. This can be predicted or given by the n+1 rule. But let me ask you this. What about the 2 carbons between there, here and here? Carbon is NMR active. Or is it? Only C13 is NMR active, not carbon 12. Carbon 12 does not have a net spin, and thus it does not have a magnetic moment. And thus you're not going to be drawing different magnetic moments for carbon 12. That is, it does nothing. It's silent in this regard. What's the chance of this carbon being a carbon-13? Because if it was a carbon-13, that would have a magnetic moment in the presence of an external magnetic field, and we can do these scenarios. But there's only a 1% chance in a given compound that that's going to be a carbon-13. If that was carbon-13, it would split the signal. But it's so unlikely for that to be a carbon-13 that we just do not see splitting for carbon, or by the carbon, nor by that carbon. Also, many other atoms simply do not split for various reasons, which we really do not want to go into at this introductory level. So ultimately, the only thing that's going to split the CH3 signal is the H in this compound. Typically for us, only hydrogens are going to split the signal. If something else splits the signal, we will probably most likely point it out and discuss. Okay. Important here, though, the H's that are splitting must be equivalent. If they're not, we're going to have to consider some other things. All right. Back over here. Wanted you to be working on this, filling in the multiplicity here, the splitting. But we can ask a question. Signal A for the CH3, what would we expect it to be? Singlet, doublet, triplet, quartet, multiplet? Well, signal A has two neighbors that are within 3 sigma bonds. Two neighbors. N plus 1 would be 3. A would be a triplet. Okay? So, you can work towards filling the rest of these in and also identifying where is this triplet in the spectrum. Okay, splitting, very fascinating, but the splitting is also very useful. Very useful, because you can just look at the splitting and you can tell. What can you tell? You can tell how many neighbors are there, because the neighbors do the splitting. Okay. Along with the splitting, we want to look at something called coupling constants. The coupling constant is the distance between the lines of a split signal. Okay? And this distance can vary. The distance is known as the J value. For example, 2 doublets shown here. The 2 lines of a doublet can be relatively close together, or the 2 lines of a doublet can be further apart. We say that in this A doublet, B doublet, the B doublet has a greater coupling constant. Greater splitting, but typically we call it the coupling constant, or a greater J value for the B doublet. Now, the distance can be stated or given. It's usually given in hertz rather than ppm. We'll look at an example. First, let's just look at a table of coupling constants. With alkanes, okay, if two different H's are splitting each other, by the way, the terminology is splitting each other because if B is splitting A, then A has to split B. Just back over here. If this signal is split by the H, then the H signal must also be split by the methyl. Okay? And so we say that these two are coupled to each other. Okay. Now the coupling between an alkane hydrogens, adjacent neighboring alkane hydrogen, is typically about 7 Hertz. Now if you're writing a paper or something or listing your data, you call this a J value. You would call this J. You can also indicate or clarify what H's you're talking about or something. In this case, we can say JAB. The coupling between AB equals 7 Hertz. Now, Hertz is a unit of frequency. Okay? All right. Well, this is interesting. These two H's, the coupling is going to be 0. These are not coupled. There's no coupling. Why? Because they're greater than 3 sigma bonds from each other. They're not close enough to be coupled. Okay? 2 or 3 sigma bonds away is the maximum. We can only get further coupling, longer range coupling in some pi systems. But with just standard sort of alkanes or sp3 CHs, there's not going to be any coupling when there's 1, 2, 3, 4 sigma bonds separating the nuclei. Okay. 2 H's on an alkene carbon, if they're different, will be about 2 Hertz. Geminal. Geminal meaning twins. They're on the same carbon. This assumes that A and B are different. All right? If these 2 H's were the same, they would not be coupled to each other. Identical H's do not couple. They do not split each other. Because it's the same signal. Okay. We'll look at these here. But first, let's look. This is an example of long-range coupling. 1, 2, 3, 4 sigma bonds away from each other, like this. But because there's a pi bond in here, it does sort of promote the coupling of these. But look, the coupling is very small. Considered a small coupling. 1 Hertz. Okay? So that is an example of a longer range coupling beyond 3 sigma bonds. But let's look at these H's here. This is an alkene, and here the H's are trans. And here, well, trans, and here they're cis. Okay? And these would be considered vicinal, okay? Vicinal hydrogens. They're in the same vicinity. They're not twins on the same carbon, but they're adjacent to each other. Vicinal trans hydrogens are going to have a coupling of about 15 Hertz. And vicinal cis hydrogens, the coupling will be smaller at about 10 Hertz. Now we're not going to go into why the coupling is different at this level, but we'll just make this statement. Now, how can we use that information? If we had 2 compounds like these 2 here, these 2 carboxylic acids with the alkene, Here the groups are trans, and thus the H's are trans. Here the groups are cis, and thus the H's are cis. You would be able to distinguish these two compounds by NMR. Now the two H's are very similar. These two are very similar to these two. So peak position is not going to help you distinguish them. Or integration, because they're each 1,1 and 1,1. What can help you distinguish these two compounds is the coupling constant of these two H's. By the way, this will be a doublet, and this will be a doublet. Why is this a doublet? Because 3 sigma bonds away there's an H, and this H will be split by that H by the n+1 rule. One neighbor, n+1 is 2, doublet. This guy also has a 1H neighbor. n+1 is 2, doublet. This will be a doublet, this will be a doublet. The difference in these two compounds, though, is when the H's are trans, the coupling, or the distance between the lines of your doublet, will be greater. And here it's 14 Hertz, where when they're cis, it's going to be less than that, and here they're 9 Hertz. Now these 15 and 10 was approximate, okay? In this real life example, we have 14 versus 9. So the coupling constants can help you assign compound. Okay, here's something for you to do as practice. Determine the J value in Hertz for the most upfilled doublet. I'm actually giving you the peak position. I could maybe ask you to find the most upfilled doublet. All right, and the HNMR of this compound. And the HNMR of that compound is given on the next page. And the most upfilled doublet is, first off, this is a real life NMR. Okay, it was obtained here using our NMR at AU. We can sort of look at it for a moment. Baseline, the exact peak positions are given above the signal. So we see this is approximately just above 10, but the exact peak position is 10.09. All right. And by the way, in NMR, usually you just stick to 2 decimal places, at least for proton NMR, 2 decimal places. In carbon NMR, it's standard to go with just 1 decimal place. So 10.09, or we could round this off to 10.10. Basically, this is your exact ppm. Here, the integration is given below the baseline. Here, so this is the integration for each signal. These 3 signals were integrated all together. Separate integration. Okay, a real NMR is going to show a peak for your solvent. This is DMSO D6, if you remember solvents. Now, DMSO D6 does not have any hydrogens, and that molecule does not give a signal in the HNMR. What gives a signal is some residual hydrogens on the DMSO D6, okay, because this is only like about 99.9% D. That is, you probably have some solvent molecules which have maybe, I'm going to draw this CD3. You probably have some molecules where there is only 5 deuteriums, and then you have a few molecules that have, well, only 5 deuteriums, and then thus it has 1 H on it. Or you could have a molecule that has 4 deuteriums and maybe 2 H's. Okay? It's not 100% deuterated. And this residual proton that sits here will give you a signal. And that is, when we say the solvent signal, it's really the residual hydrogen in your deuterated solvent that's giving the signal. Now, if this was complete hydrogen, all right, 6 hydrogens, this signal would be like a mile tall, and it would make the other signals quite small relatively. And that leads to practical problems related to noise in your spectrum. All right, but a small solvent signal is okay. We also have water in a real NMR. Water is everywhere, including in the atmosphere in which the light is traveling through. It gets absorbed by your compound, but it can also be absorbed by water that's just in the atmosphere. There's also probably water in your DMSO because it's a very polar solvent, and so it's not 100% dry. Water will give a signal. In DMSO, that signal is about 3.3 ppm. Now, on the very back of the handout, I include a sheet which tabulates peaks for common solvents and water. All right? DMSO D6. It gives a signal at 2.49. All right? 2.49. In the proton NMR. And then water in DMSO gives a signal at 3.3 ppm. 3.33. And this water signal is about 3.3 or 3.4. That can vary slightly. There. Okay. So, there's some important information here. It's very practical information. All right. So, back to the coupling question, coupling constant calculation. Determine the J value in Hertz for the most upfield doublet. I'm telling you it's about 7.02 ppm. And that is actually right here. Okay, about 7.02 ppm. It is a doublet. Now it can be hard to see that it's 2 lines, but the labeling of the peaks gave you the ppm value for each line, clarifying for you that it's a doublet. Now the peak next door is also a doublet. All right, but the most upfield doublet would be this guy here, and the question asks you to calculate the J value for this doublet. All right, now again, let's review a little bit. The J value is just the distance between your 2 lines. All right, the distance between the 2 lines in ppm can be given just by subtracting your 2 ppm values. And so that is 7.033 ppm minus 7.021 ppm equals the difference in ppm 0.012 ppm. That's the width of the doublet. But J values are given in Hertz, not ppm. All right. The reason being is because J values are constants. And we haven't talked yet about why we use ppm. If we gave J values in ppm, the J value would change with different instruments. All right? We are using an instrument that is 300 megahertz. That's the operating frequency. That's the size of the instrument, okay? This can vary. More money, bigger the value here. 500 megahertz. That's sort of the top entry level. 800 megahertz. This effectively is going to bigger and bigger magnet. All right? It leads to greater sensitivity. We'll talk more about that. But as this changes, ppm would change if your J values were given in ppm. But if we give them in hertz, the hertz value will not change if you change the magnet size. So we give it in hertz because it's more of a constant when given in hertz. Okay, basically the job for you to do is this equals how many hertz. All right? Convert ppm to hertz, and that will be your answer for the coupling constant of that doublet. Now, I say here to convert ppm to hertz, see your textbook. All right? And I've already told you that the NMR of this compound was obtained at 300 megahertz. All right? So give that a try. Okay. By the way, this compound was made in my research lab as a potential antiprotozoal compound for treatment of diseases such as malaria or African sleeping sickness. Or leishmaniasis. Okay. All right, let's look at complex splitting. Now, it's not really overly complex. It's just a little more involved than sort of our simple splitting that we've covered in the previous couple of pages. All right, first review. This is standard splitting here. This signal will be a triplet because there's two neighbors. All right, two H neighbors. N plus 1 is 3. That signal would be a triplet. This signal would also be a triplet. It also has two neighbors. It's got one on this side within 3 sigma bonds, and it's got one on this side within 3 sigma bonds. And importantly, those two H's are the same. Okay? Same. Look at this. It's a very symmetrical molecule. These H's bonded to a carbon, each with 2 chlorines. They're the same. Since they're the same, we can just count those as 2. N plus 1 is 3. Triplet. That is, the two scenarios like this are going to be the same if the H's are the same. On the other hand, let's look at this compound. This signal will not be a triplet. It has two neighbors within 3 sigma bonds, but they're not the same in this case. This one's bonded to a carbon with 2 chlorines. This is bonded to a carbon with chlorine and bromine. Not the same. So if you look, first we'll do theory here. If you look at the possible magnetic moment directions for the two H's, they can both be lined up with the external field. They can both be opposed. One can be lined up, one can be opposed. Or you can have the other one lined up and the other one opposed. Now previously, these two scenarios were the same, identical energies, identical net magnetic moments when combined. Over here. But over here, they're not the same. That one lined up with the external field is different from this one being lined up because the H's are different. not the same. You have 4 different possibilities here. So you're going to get 4 lines. And the ratio will be 1, 1, 1, 1. Where this ratio will be 1, 2, 1. And it will be 3 lines triplet. Okay. How do we get to 4 lines? Well, that's the theory. We can also look at this in this manner. When H's are different, you must do the splitting separately. They're different. First, let's look at how this H is going to split. This H splits this signal into a doublet. And that's what I'm showing here. The original signal, if it was not split, would be split into a doublet. Then, each of these theoretical lines is then split into a doublet by the other H. And so this becomes a doublet, and then this line becomes a doublet, and this one becomes a doublet. And that's another way of looking at it, of how you get 4 lines. Ultimately, non-equivalent H's split differently. You have to do the splitting twice. You apply the n+1 rule for each type of neighboring hydrogen. All right? You cannot combine these. Many students will look at this and say that should be a triplet because of 2 neighbors. And they would be wrong. All right. Now, some books, some instructors may let sort of students get away with this. All right? But if you really want to learn the theory of splitting, you need to pay attention to this. And again, ultimately, we're just applying our n+1 splitting rule twice here because the H's are not the same. Okay, let's do some practice with this. What type of splitting or multiplicity would we expect for this CH2? All right. Well, it has 4 neighbors within 3 sigma bonds. Does that mean it's going to be 4 plus 1, 5? And 5 would be 5 lines. We might call that a pentet. But when it's beyond 4, we just call it a multiplet. It will not be 5 lines. It will actually be 8 lines. Why? We do this splitting separately. First, the CH3 is going to split this into a quartet. n+1 is 4, quartet. So we split the signal into a quartet. Now we come back and we split by this neighbor. 1, 2, it's within 3 sigma bonds. That will split this signal into a doublet. n+1 is 2, doublet. And what that effectively does is each line of this theoretical quartet will become a doublet. So that one becomes 2, this one becomes 2, that one becomes 2, and this one becomes 2. And your signal will look like this, and that's actually 8 lines, not 5. Now in both cases we may call this a multiplet. But if you're able to count the lines, if your NMR is resolved enough to see the individual lines, there should be 8 there, theoretically. Okay, let's do one more. And then you can do the rest here yourself. What splitting do we expect for this H? Well, there's a neighbor here within 3 sigma bonds. We'll call that HA. And there's a neighbor here within 3 sigma bonds. We'll call that, is that the same as that one? No. This H is neighboring chlorine. This H is neighboring bromine. So this is different. We're going to call this B. 2 neighbors. 2 plus 1 is 3 triplet? No. They're not the same. You cannot just lump them together. Remember? They must be equivalent to lump them together as a single n+1 rule. We have to apply the n+1 rule twice. Let's first consider the splitting for HA. Here's our original signal. HA is going to split this into a doublet. Okay. By the n+1 rule, n+1 equals 2, doublet. Now we come back and split each of these lines by HB. There's only one of these. And that's going to split each of these lines into a doublet. Boom. So each line becomes a doublet. And the signal is going to be 4 lines. Okay, that was a 1 and 1 splitting. Where up here we had a 3 and then 1 splitting. 4 lines. All right. Now, importantly, is that a quartet? The answer is no. We don't call that a quartet. All right. A quartet is going to look like this. Remember, 1, 3, 3, 1. This is called a DD. That stands for a doublet of doublets. All right. Each line is going to be approximately the same height. All right. You try these other 3 here. All right. Don't write so much on your paper there like I did, because you're going to have more to do and you want to have your own writing. Okay, I've mentioned that before. All right, we just call this complex splitting. It's basically just splitting twice. And I suppose you could have a compound where you needed to split 3 times, but that's going to be probably more rare, especially for us. All right. Looks like we can now take a look at the D2O Shake. But at this point, you can start going back, sort of trying to make assignments here. Triplet. Okay. This is something we should maybe do at this point. Sort of go in reverse and ask, very important when you want to come up with structure from a spectrum. Why is this signal a triplet? And how many H's is this signal for? What's for 2 H's? That's the integration, okay? There's no integral line, but I'm giving you that. It's a CH2. Now, it could theoretically be 2 CHs that are identical, but it's a CH2. That's the integration. What does the triplet part tell you? Very importantly, it tells you about the neighbors. How many neighbors does this CH2 have? Okay. It turns out that it has... Now again, we're sort of assuming it's sort of CHs here, hydrocarbon. It turns out that it's got 2 neighbors. Or 2 equivalent neighbors. That's what makes it a triplet. And so it's a CH2 neighbor. And so this is the signal. But that signal also tells us what the neighbor looks like. All right? That's the power of the splitting in your NMR. All right? We'll talk more about that once we start doing problems, solving structures. Okay. One other thing about the splitting. We've only talked about CHs. Actually, I'm not going to do that. We'll wait until we talk about those maybe in class on that page here where you're going to work these on your own. Let's finish up with this video by looking at the D2O Shake. Okay, number 5 here. The D2O Shake is a commonly used method to identify signals that belong to exchangeable protons. Exchangeable. Exchangeable protons are typically OHs and NHs. Exchangeable protons are protons that can be sort of bounced around between different O's and different N's. A CH is not acidic, typically. It's not sort of going to ionize or disionize and generate H plus or any of that acid-base chemistry. But OHs and NHs can be sort of slightly acidic, and they can participate in hydrogen bonding. And they are said to be exchangeable. Now, we'll explain this further, but if we add D2O here, we can identify exchangeable protons because the H will be replaced with a deuterium. First mechanism. Well, we can sort of protonate the oxygen with the D2O. Now that's a very poor equilibrium because this is not that acidic. But we can show this sort of protonated version, all right? And at this point, now we produce OD minus, and this oxygen anion can then come back and take the H and leave the lone pair, and we end up with a deuterium on the oxygen instead of an H. And so we've exchanged the H for a deuterium, and we've created H2O. HDO. Now, importantly, the signal for the OH, when you do this, will disappear because now it's an OD. And the OD is not going to give a signal in the proton NMR. And OHs and NH will do this chemistry, and thus they will disappear in the NMR. Now, in practice, they don't entirely disappear. They often just diminish in size. Now, CHs typically are not going to do this chemistry, and CHs are not going to exchange, and thus CHs would never diminish in size. Let's see how this can be used in NMR. Let's turn over here a couple of pages. Not that one. Yes. It says number 5, D2O Shake. It's sort of been cut off up there. This is another compound from my research lab. Here's the proton NMR. Aromatics, 7 to 8 region. Okay. We've got H2O, remember water, about 3.3. This is DMSO, residual solvent. The remainder is compound, all right? Aromatics. This looks like a doublet here. It's actually 2 singlets. That's the 2 methyl groups. They're not equivalent. Each one gives a singlet. Sort of down in the 1 to 2 range. This is actually a little impurity. Because otherwise the baseline should be flat. And this is an example of how NMR is very good at showing impurities or showing purity of your compound. All right. Now, aromatics, methyls, two more signals. We got a CH2 and an NH2. Both integrating for 2. They would both be singlets. Why? There are no H neighbors within 3 sigma bonds from here or here. Okay, make sure you know why these would be singlets. Here are your 2 singlets. The question can be, though, which one's the CH2 and which one's the NH2? We can answer this by doing a D2O shake. We run the NMR. Okay, this goes into the magnet. We run our NMR. We print it out. Then we go back and we open up the tube and we add in a drop or 2 of D2O. And we shake it so it can mix. Okay, and as it's mixing, that chemistry that we just talked about takes place. And any exchangeable protons will exchange with the deuterium and become D instead of H. All right? Now only the NH2 will do this because it has a lone pair and it can react with the D2O. The CH2 is not going to do this. Okay, so after we do the D2O shake, we rerun the NMR. And I actually did this. And this is what the NMR looks like after you shake it with D2O. And what we notice is, of the 2 signals, the one that's more downfield is the NH2. We can clearly see that. It has diminished in size. The integration is no longer the same. This is integrating much lower. Why? Because the NH2 exchanged with deuterium. Now if it's NH2, it can actually exchange once and then it could exchange again. But we have removed H from the NH2, and if it exists like this, there's going to be no signal at all. Basically, an equilibrium is set up like this depending on how much D2O you add. You're probably never going to force it all the way here. But as it goes to the right here, you diminish the amount of H that's there and the signal gets lower. All right? Where the CH2 did not diminish because it's not exchangeable. So the D2O shake helped us determine that the more downfield signal here in this case is the NH2. Or at least that's pretty good evidence. All right? Now in my example we did it with an NH2. You can also do this with OHs. Okay. I think that's going to finish up the video here. In the next video we will start doing practice problems. Basically this one here can be our first one. Now Bruce was an older textbook. This came from the Bruce textbook, so unless you're using the Bruce textbook, you're going to just probably ignore such. The question really is, determine the structure here. What is the structure of this compound? Formula is given in this case. Later on we will not even have formula. Alright, looks like it's just a hydrocarbon. Basically you need to remember what each signal tells us. For example, what type of H's give signals in the 7 to 8 range? Because this is a proton NMR. We're only looking at H's. What type of H's give signals in this range? Your integration is given by an integral line. Remember, we need to cut that like this and measure it. Integral line. Some peaks have been expanded. For example, this one at about 1.5 has been expanded here. So you can see the number of lines clearly. 1, 2, 3, 4, 5, 6, 7, 8 lines. Okay? That may or may not be critically important. They're just showing you that. Peak position, what does the splitting mean? Okay, that looks like a triplet. It's expanded here. Clearly a triplet. But for how many H's? H's needs to come from your integration. What makes that a triplet? What makes that a multiplet? And then we need to consider this peak. We also have things like degrees of unsaturation. Remember that. Because if you're given formula, you can use DUS, and that can give you some structural information. I will also give you some sort of working hints. Okay? But what I want you to do first is give it a try on your own. Then I will give you some practical working hints, some tidbits here, some so-called free information. Okay, and we'll sort of pull it all together to determine structure here. Okay, and there's a couple of others in the handout. We'll also be moving in the next video to carbon NMR. Okay, there'll be lots of similarities there. We'll just be focusing on the carbons. Okay, guys, stay tuned for the next video. Please be working problems.